and we'll talk about 3 arguments for a wave function realism. So please, Alyssa.
Okay, thank you. Great to see you all. So I'm going to be talking about this view, wave function realism. And as the title says, most of the talk is going to be concerned with laying out what the arguments are for wave function realism. In particular, I'm interested in clarifying, there have been many different arguments presented for wave function realism in the literature, and I feel like some of them are just clearly not compelling, even ones that I've presented in earlier work of mine. And they're not compelling in the sense that they don't do anything to tell us why we should prefer wave function realism over any of the really serious rival positions that people want to defend in philosophy of physics. So I'll present those other arguments just to say, you know, we should put these aside. There are maybe nice starts at telling us we should be realists about something, but they don't do a good job of really getting us to this more stronger position. That's wave function realism. And then I'll talk in more depth about the argument that I do take to be compelling. Okay. So let me just start by clarifying what I'm talking about when I say wave function realism. So when I talk about wave function realism, I don't mean a particular metaphysics. So like a view that there is this wave function that has a certain kind of features and lives on a particular kind of space, but rather a kind of framework for providing ontological interpretations of different quantum theories. So a framework that you can plug into different quantum theories that'll lead to different specific ontologies or different specific metaphysics. But those ontologies will have some common structure. So in particular, when we're talking about wave function realists interpretations of quantum theories, those are going to be ones in which the central object or a central object, if we're talking about interpretations of hidden variable series, is the wave function. And this view isn't just that the wave function is real, but that the wave function is a particular kind of thing. It's a field on a high dimensional space with a structure of a configuration space. And then what that configuration space is will depend on the quantum theory that we're trying to interpret. So this is a view that the way I see the history is, it was a view that is somewhat like something Schrödinger wanted when he wanted to replace the matrix mechanics with this wave mechanics and hope to give a theory that had this natural ontology of a wave evolving continuously and so on. But when Schrödinger recognized that this would have to be a field on a high dimensional space, he said, no, thank you to this. Later, it gets explicitly endorsed by Bell in his discussions of Bohmian mechanics and spontaneous collapse series, and then taken up by philosophers of physics, David Albert and Barry Lower in '96. Albert in his paper Elementary Quantum Metaphysics, and Lower endorses this at the end of his paper Humean Supervenience in '96. And then I've been trying to defend the view and develop it for a little while. Jill North also defends it, but I consider us, to have still a very minority position in terms of views about the ontology of quantum mechanics. And so a lot of the work that I've done has been to try to defend this view against objections, but that's not what I'm going to do today. I'm going to be trying to give the positive view. So if you want to raise objections to it, you can in the Q&A, but I'm mostly going to be concerned with getting clear on why we should take wave function realism seriously. So as I said, it's a framework for interpretation, so it's going to apply to different quantum theories and yield different particular ontologies. But the wave function realist, since usually wave function realism is proposed in the context of some kind of scientific realism, they're caring particularly about quantum theories that can allow solutions to the measurement problem, right? So theories that are going to allow us to connect theories to the real world, the world we observe. All right, so that's the view, that's the framework that I'm trying to defend here, or get clear on why we should defend it. So the 3 arguments I'm going to call the prima facie case for wave function realism. I call it that after we'll see a quote from Peter Lewis that kind of presents it that way. Then I'll talk about another argument I call the argument from entanglement. And then finally, the argument that I take to be like the good argument is going to be the argument from separability and locality. And yeah, so I have references to where I see this work. So I think the good argument is something that I do find in Barry Lower's paper on Humean supervenience. And in recent work of David Albert's, his paper, How to Teach Quantum Mechanics, that he's been circulating, I do think that he's giving something like an argument from separability and locality, though it's a little bit tacit in there. But I'm not going to be concerned with David Albert exegesis here, just trying to, if you're familiar with his work and want to see like, how does this relate to things he said? I think the newer arguments that he's giving are more like moving from something like separability and locality, though they're much more interesting than just that. So I'm not going to try to give his argument. I'm going to give the argument the way I see it to be most compelling here. All right, so the prima facie case for wave function realism is just basically when you look at different versions of quantum theories and their mathematical formalisms, the ones that solve the measurement problem, these all make central use of wave function representations. And then there's central laws or laws describing the evolution of this wave function over time, or possibly, in the case of hidden variable series, how the state of the wave function affects the evolution of other basic entities in the theory. And so if we just interpret this literally the way that we might want to interpret, say, like classical theories literally, this suggests there is this entity that wave function representations are describing, and it's a wave function. So, here's a chart with different solutions to the measurement problem, and their state representations and their laws of state evolution. In each case, you have a wave function providing the central state representation, and then you've got laws of evolution, Schrodinger equation, or a stochastic GRW equation, which just describe the evolution of the wave function over time, or the guidance equation, which describes how the wave function affects something else in the theory. So I take this to be this kind of argument to be what we see in Albert. Also, this is what I would read into Bell when he talks about, we have to understand the wave function as a field on 3n-dimensional space, and his in the Impossible Pilot Wave paper and others of his other papers of his. But here's David Albert in '96. He says it's been essential to the project of quantum mechanical realism in whatever particular form it takes to learn to think of wave functions as physical objects in and of themselves. And then you can ask, well, what are these things? The sorts of he continues, the sorts of physical objects that wave functions are, and this way of thinking are plainly fields. Okay. And then the argument, I think, is even more clearly presented in Peter Lewis's paper from 2004 called Life in Configuration Space. So he says here, the wave function figures in quantum mechanics in much the same way that particle configurations figure in classical mechanics. Its evolution over time successfully explains our observations. So absent some compelling argument to the contrary, the prima facie conclusion is that the wave function should be accorded the same status that we used to accord to particle configurations. Realists then should regard the wave function as part of the basic furniture of the world. This conclusion is independent of the theoretical choices one might make in response to the measurement problem. It's a wave function that plays a central explanatory and predictive role. Okay, so far I say this is just a prima facie case. So I guess maybe what I should say is, it's not like I want to say this argument does nothing for us. It's just, the problem is all this gets us to is we should take wave functions with ontological seriousness. Just like, we took particle configurations in classical mechanics with ontological seriousness. But it doesn't yet get us to the conclusion that the wave function is a field on a high dimensional space. Albert says plainly, this is what these things are. But given the fact, the dialectical situation we're in philosophy of physics now, where we're debating all of these different interpretations of wave function representations, just saying that wave functions, the central representations of states and the laws are in terms of wave functions isn't enough to tell us the wave function is a field on a high dimensional space. So what we need is an argument that give us some reason to prefer wave function realism to other interpretive approaches. So we need to go beyond this prima facie case. All right, so the argument from entanglement was an argument that I tried to develop earlier and influenced by others. Jill North gives a similar argument as well. That was trying to say, yeah, we're going to start from the idea that there are these wave functions, but then we're also going to say, and it's not possible to interpret the wave, if you want to make sense of quantum theories, it's not possible to interpret those wave functions in any other way than as fields on a high dimensional space. So the idea for this argument was, it's not possible to give a metaphysics for quantum theories which distinguishes empirically distinct quantum states. So distinguishes different entangled states, or distinguishes some entangled states from separable states without interpreting the wave function as a physical field on a high dimensional space. So let me just try to give you the flavor of this argument a little bit. So the way that I usually start in presenting this argument is to try to start with a kind of natural view you might have about wave functions that doesn't understand them as fields on a high dimensional space, but just takes them to represent something like fields on a low dimensional space, like the 3-dimensional space or space-time. So, suppose we have, some particles that start out in singlet state. We send them through some Stern-Gerlach magnets to measure their z-spin, and we wind up with a system that's in this entangled state where we have 2 particles, right, that are entangled with respect to their spins and their locations. I've labeled these 4 locations A, B, C, and D. And we can ask, okay, so if we want to interpret this quantum state realistically, what is the ontology, right? What is the ontology here? And so, you could start if you wanted to remain committed to a low dimensional ontology, right? Not the high dimensional field ontology of the wave function realist, but some kind of ontology in 3 dimensions with local beables. You might say, okay, well, what we have here, we have 2 fields, one corresponding to particle 1, one corresponding to particle 2. And the first one is, smeared out with half of its intensity at location A and half at location B. And then the other one is smeared out with half of its intensity at location C and half at location D. But the complaint is, well, that doesn't distinguish the state from other empirically distinct states. So we could talk about other Bell states. We could also talk about, just separable states like this one, psi prime, that I have on the bottom of the slide. In this case, also, if you want to understand wave functions as low dimensional fields that are spread out, over locations in 3-dimensional space, again, you would say the same thing, that you've got, 2 fields. The first one's half at A and half at B, and the second one's half at D and half at C. And there would be nothing in your ontology that is distinguishing, these 2 states that are measurably distinct states. So the solution here, this is what the argument from entanglement says, is although it's not possible to distinguish these measurably distinct states in a low dimensional field representation or a low dimensional wave function representation, if you say what the ontology of the system is 2 fields in low dimensional space, but instead you say it's 1 field in a high dimensional space with the structure of a configuration space, then you can distinguish, your ontology does distinguish these 2 states. So in one case, we'll say there's there are these 4 locations corresponding to, particle 1 at A, particle 2 at C, A, D, and so on. And when we have the first quantum state, that means the wave function only has amplitude at the 2 locations A, D, and B, C. And in the quantum state psi prime, we've got 4 locations, all 4 locations, the wave function has some amplitude. So that's good. So that gives us, I guess, somewhere. Now we're saying, well, wave function realism is a better interpretation of wave functions than this simple fields and 3-dimensional space interpretation of wave functions. But okay, I have a couple quotes here where this argument's given by Jill and me, but let's just, in the interest of time, I'll keep going. I won't read the quotes. But the problem is that it isn't true that entangled states can only be distinguished in a high dimensional ontology. There are rival ontological approaches. Many of their defenders are here today. Nobody, to my knowledge, defends this simple wave functions are fields smeared out in three-dimensional space view. And all the alternative views that are taken seriously today have the resources in their ontologies to distinguish these different states. So apologies if your preferred view is not on this list, but I'm trying to list most of the views that have been defended. So let me just say, I meant to say this earlier and I didn't. Everything I'm saying is supposed to be in the context of realism. Okay, so that's, I mean, the prima facie case for wave function realism was starting with this idea that we're going to be realists about quantum mechanics. We're going to interpret quantum states as representing something objective about our world that exists, whether anybody's observing it or not. And these are all rival approaches that interpret wave functions realistically. That's not to say I don't think that there's other important work for the wave function realism in justifying the realism in the first place, but that's just not what we're trying to do here. I think what I'm looking for is an argument to prefer wave function realism as a framework for giving ontologies for quantum theories that is preferred over these other rivals: primitive ontology approach, wave function as property view, ontic structural realism, and all the rest. Okay, so this is what I think the argument from separability and locality is able to do. Okay, so here's how that argument works. So the argument from separability and locality says wave function realism is unique in yielding pictures of the world with two intuitively nice metaphysical features: separability and locality. Although the pictures of the world yielded by the primitive ontology approach, holism, structuralism, space-time state realism, and the rest may be made empirically adequate, they fail to provide pictures of the quantum world that are fundamentally both separable and local. Interpretations of our best physical theories that are both separable and local yield theoretical and practical benefits, and this is a reason to favor wave function realism as an approach to providing metaphysics for quantum theories. All right, so let me unpack these premises a little bit here. So when I'm talking about separability, this definition, I tweaked it a little, but that basic idea is coming from Don Howard in his paper on separability and locality in quantum mechanics from the 80s. So, okay, so for metaphysics to be separable, you need two conditions to obtain. The first is that your metaphysics has to include an ontology of objects or other entities that are instantiated at distinct regions, each possessing their own state. So if you don't first have at least like multiple regions and whatever the space is of the theory with distinct entities there, or distinct property instantiations, or some kind of ontology at distinct locations, you can't have separability to begin with. The second condition, though, is that, and it will also be the case, that whenever you have objects or entities instantiated at distinct regions, R1 and R2, all categorical facts about the composite region, R1 union R2, are determined by the facts about properties and objects instantiated at R1 and R2 individually. So to have a separable ontology in this sense, it can't be the case that there are, for example, any relational facts about R1 and R2 that are not grounded or determined by what's happening at the individual regions, right? So for most of the rival approaches, and this isn't like, they're upfront about this, they're completely transparent about this. Most of the other alternatives, the way that they're able to distinguish different quantum states is by positing some kind of non-separability. So, the simplest kind of example would be like Paul Teller's relational monism, and my colleague Paul Teller's relational monism. So in that view, you have the way that you're distinguishing these distinct quantum states is you have these relational facts. So when particles are in the singlet state, it'll be the case that they have opposite spin, even though that's not grounded in any intrinsic facts about their individual spins, because they don't have individual spins. Nonetheless, there is this relational fact that obtains. And then the different views have different ways of getting rid of separability. Howard's view rejects the first, at least the way I understand it. You just say they're not distinct. The particles aren't distinct, so you don't have these separate objects at separate space-time regions on that view. So by contrast, although most of these alternatives, let me just go back to that list. Although most of the alternatives to wave function realism wind up, having metaphysics that are empirically adequate by rejecting separability, that's not true for all of them. So the primitive ontology approach is one that I would argue does have separable metaphysics, at least in terms of the matter of the theory. They have this other thing in their ontologies, a wave function, but that's not part of the matter of the theory. It's something that plays a role of something like a law that guides the ontology. But in terms of what's happening, how things are laid out in space, the primitive ontology approach does have a separable ontology. So what it would have to say for that one is, although it doesn't give you a separable ontology, or it does give you a separable ontology, it doesn't give you a local ontology. And that's their strategy. That is what they do. But let me just, I guess I'll finish this slide. So, right. So most of the other alternative ontology or frameworks for giving ontologies for quantum theories do give up separability. The wave function realist has a completely separable ontology. And so the reason is that in the high dimensional space of the wave function, all facts about what happened at composite regions in the wave function space are determined by facts about the wave function at the individual regions. And then same thing, if we're talking about a wave function realist interpretation of Bohmian mechanics, all facts will be determined by facts about the wave function at the distinct individual locations of the space, plus the location of that one marvelous point in the high dimensional space. It is true that if we want to talk about a low dimensional ontology, so generally wave function realists aren't nihilists about the three-dimensional world. They just think the three-dimensional world isn't fundamental. They think it's somehow a derived or emergent metaphysics. There you will have non-separability. But if you just confine yourselves to facts about the low dimensional space. But the claim is all those facts about relations that don't bottom out in facts about the relata in the low dimensional space can ultimately be explained or grounded in facts about the wave function in the high dimensional space. Okay. So we do have a separable ontology there. All right, locality. So the argument is that wave function realism is unique among realist ontologies for quantum mechanics in that it provides ontologies that are both separable and local. So by local, I mean here contains no action across spatial distances. And so in this case, again, it will be, this is my note at the bottom of the slide, it will be the case if you just look at the low dimensional ontology that there will be, assuming what version of the quantum formalism you're looking at, but on many you will have non-locality in the low dimensional image. But when we talk about the fundamental image, the fundamental picture of the universe that, that wave function realists give, those will all not contain locality. And so the wave function realist will reveal the apparent non-locality manifested by quantum mechanically entangled systems to be a consequence of a more fundamental metaphysics that's local in higher dimensions. I just want to say this isn't trivial. So, I could have had the whole talk be about this. It's something that you have to argue for each case. I think it's the most straightforward in the case of Everettian quantum mechanics, but it's not going to be straight, that's not necessarily the case on all approaches. In particular, for spontaneous collapse approaches, there may be reasons to worry that actually you don't have non-locality in the wave function realist metaphysics either. I think you do. So in the case of these spontaneous collapses, although it will be the case in the low dimensional image that Alice's measurement immediately affects the state of Bob's system, or the measurement Bob's going to make, or the result of the measurement Bob's going to make. When we move to understand that in terms of the high dimensional space, both Alice and Bob are somehow reflected in each of these different points in the configuration space. And so there, what's going to happen isn't that something in this one part, right? I guess Alice's Bob is up and Bob's particle is down part immediately causes something to happen in the other part of the high dimensional space. Rather, what's going to happen is there's going to be a immediate hit on the wave function, and both of these systems change immediately, but not that what happens over here causes what happens over here. I can talk about this more in the Q&A if people want to, but the argument is supposed to be in the high dimensional space. If we think about things carefully, it's not going to be the case that the wave function metaphysics is a non-local metaphysics. It's a local metaphysics where things in one region of the high dimensional space do not immediately affect what's happening in other regions of the high dimensional space. But in virtue of this evolution of the wave function in the high dimensional space, you manifest this appearance of non-locality in the low dimensions. All right, so far I've said, this is the first part of the argument, the wave function realist is unique in being able to provide metaphysics for quantum theories that are realist and both separable and local, at least fundamentally. Now you might say, who cares? Why do we want metaphysics that are separable and local? And I think that is like a very important question to answer. If we shouldn't care about separability and locality, and I mean, when I read a lot of the papers of people defending alternative approaches, it often seems like that's kind of what they're saying sometimes. Why care about that? So I think that should be the job of the wave function realist to give an answer to that. So there are different arguments that you can find or come up with for why we should prefer metaphysics that are fundamentally separable and local. And so I've arranged these on the slide, starting from ones that are more empirical looking arguments to at the bottom, the ones that are the most a priori looking, right? The most armchair metaphysics kind of arguments. So the first two are both arguments that are associated with Einstein. So the first have in mind kinds of things that Einstein said in his paper Quantum Mechanics and Reality, where he's talking about the kinds of physical reasoning that we're familiar with, that's been successful, have been forms of reasoning where we take entities to be spread out in space, right? And they each have their own kind of features at these different locations in space, or the best example of what he had in mind was a field ontology. He also there talks about locality, assumptions that the metaphysics is local have been very useful in giving physics the success that it's had. The second argument is also, I take it, so this one I'm kind of drawing on work of Valia Lori, although she would not like using this as a defense of wave function realism. She said similar things when she's defending her primitive ontology approach. So the idea coming from Einstein is that we should see our scientific theories as refinements of the manifest image. And so, we start from the manifest image when we're trying to, develop our scientific theories and then depart as little as possible from them. And so, Valia uses that to argue for a primitive ontology approach where the basic ontology looks very much like the ontology of classical physics. But I think that you could also use this to argue for, separable or local metaphysics that are, manifest image or earlier physical theories had ontologies that were, or metaphysics that were separable and local. And so, it's best to kind of depart as little as possible from that. Now I'm going to put X's through both of these, because these arguments, although they're nice, are not going to work for a wave function realist. One, when Einstein's talking about the success in having metaphysics that are separable and local, he's talking about separable and local in low dimensions, in 3 dimensions, right? So we can isolate what's going on here and know or do things over here and be confident that they're not going to be messing things up over here in 3 dimensions. So that argument's not going to work. And the second argument also, this is why I think Valia laughed when I took her ideas and applied them to wave function realism. That doesn't work either, because the wave function realist metaphysics are super radical. It's fundamentally the world is a field on a high dimension space. That doesn't look anything like the manifest image. So those ideas aren't going to work. So what are we left with is our armchair metaphysics. But I don't think that's so bad. So there are 2 other kinds of arguments that we can give for wave function realism. So, and these are both a priori. So the first is that separable and local metaphysics are intelligible. They're intuitive in certain respects. The respects are, there are certain principles that just seem completely obvious analytic truths. So I try to write these. So the first one is, in defense of separable theories. Here's the idea: if you can't give a categorical description of one thing without appealing to another, then the 2 aren't fundamentally distinct, right? I can talk to you and talk about where you're from, if you have siblings, what sports team you root for. I could say all these things about you that are extrinsic, non-categorical. But the idea is I can also talk about you without appealing to these other things. And if I couldn't, then it seems like you wouldn't really be something distinct from these other entities. So there's this kind of, I think there is, this is something in favor of a separable and local metaphysics, or the separable metaphysics that the wave function realist gives. And then this principle, an object cannot act where it's not, that's coming from Samuel Clarke and the discussions of the non-locality that you had in Newtonian gravity, in these debates about can we make sense of that. I liked putting things this way: an object cannot act where it's not. That doesn't seem to make any sense. So if you have a local metaphysics, you're not violating that principle, and that's saying something for it. Okay, so that's a third argument. The first argument that I think that can work to support separable and local metaphysics. And the last has to do with simplicity and parsimony. So here, this is something that, so I mentioned Barry Lower earlier in his paper, Humean Supervenience. So in that paper, I mean, he's at the end, he talks about wave function realism and talks about how you might worry that quantum entanglement requires you to posit these fundamental relations, and that's in tension with Humean supervenience, because in Humean supervenience, the idea was all we have is a collection of little things instantiating intrinsic properties, and then the only fundamental relations there are the spatiotemporal relations. And so he wants to say, well, you have that if you're a wave function realist, right? You don't have to postulate these additional non-fundamental relations. You can just have little objects instantiating intrinsic properties in the high dimensional space, right? And then the spatial relations between them. And that has a virtue. So why, but you might say, well, why do I care? I don't care about being a Humean. Well, then we have to look for arguments for that. But the kind of standard arguments that when people talk about why be Humean is they relate to the simplicity, the parsimony of a Humean ontology, and that it's not positing additional fundamental relations. So that's something that you might think is interesting as well. How much time do I have left, Vincent?
About 10 more minutes.
Oh, cool. Okay, thank you. I meant to set a timer and I forgot. All right, so we have the claim that the separable, that wave function realist frameworks for interpreting quantum theories are unique in giving metaphysics that are fundamentally separable and local. And then I've said something about the kinds of arguments that might be able to support or might not be able to support metaphysics that are separable and local. And what we're left with is the arguments are arguments that are basically coming from the idea that these metaphysics are simpler, that they're more intuitive, that they're more intelligible. And so at this point, you might push back and say, why should I care about that? And so here, I guess the person who I imagine arguing with me when I think about this is James Ladyman. he had a really nice paper in the that Everett volume, what is it called, Many Worlds, question mark, where he was pushing back on people who wanted to give intelligible interpretations of quantum theories, saying like, our job as philosophers of science isn't to domesticate science, right? So we shouldn't be trying to accommodate all of our intuitions. And I think to some extent he's right. I think that we can't completely sanitize quantum theories. There is quantum awareness, and that should go without saying here. The wave function realist is defending a view according to which all of this is maybe an illusion, maybe just a non-fundamental manifestation of this more fundamental metaphysics that's a field on a very high dimensional space. But I do think that there is something to be said for preferring metaphysics that are intelligible and intuitive. So let me just, we're getting close to wrapping up, but I want to talk about that. I think that that's important. And this comes in the form of practical benefits. So there are several practical benefits that are coming from the fact that the wave function realist framework is intuitive, okay? And that's really the argument that I want to press, that it's intelligible, intuitive. The separable local metaphysics are intelligible, intuitive in this way. So I'll just list three really quickly. So, I mean, the first idea is that it allows a clearer handle on quantum theories, dissolving paradoxes when you have an intelligible metaphysics, and makes theories easier to work with. So here I'm thinking about, in analogy with what we had when we didn't, I wasn't alive, but when we didn't have to view special relativity anymore just as a principal theory, but we were able to give this kind of metaphysics of the theory as, in terms of a space-time. That allows a much clearer handle on the theory. What look like paradoxes or what look like things that were unintelligible resolve themselves into a more fundamental picture that is intelligible. And that makes the theory easier to work with. If you want to think in like a Kuhnian way, people can stop doing philosophy and start doing physics. Second, I think having these intelligible pictures are potentially useful in keeping students in physics. So lots of us that are philosophers of physics, we're physics students, and we chose not to go to do grad school right after, to go into philosophy because we were told that, you can't understand quantum mechanics, our job here isn't to understand the world, so on. And, so giving it something intelligible, it kind of cuts that off and keeps students in physics knowing that they are studying physics that have contact with reality. Then a lot of them, not everybody, but a lot of them get into the field for that way. And obviously we want more students in physics. And then finally, it opens up more questions. So these kinds of accounts, these theories can be fruitful in that they're generating more questions. If the world is fundamentally this high-dimensional space, what's its character and structure and so on. That's, I think, why we should care about having separable and local metaphysics that are intelligible is because they come with these practical benefits. But notice, this isn't to say that the other frameworks are wrong. I don't think we can know that they're wrong. And in none of my work have I tried to argue like, these other frameworks, are wrong. But the idea is that we should keep wave function realism on the table. So in the spirit of Carnap, I would advocate a principle of tolerance. Let's develop these rival frameworks. If some have practical benefits, if some have fruits, bear fruits, then let's keep them on the table and keep working and developing them and letting them be open to students that might, benefit from having these frameworks available. And so the kind of argument from separability and locality is saying that this kind of framework for interpreting quantum mechanics has certain benefits that other frameworks lack. That doesn't mean they don't have their own benefits, but this is a particular kind of benefit that these frameworks have. All right, so I just want to close with one last question because this is a question that I get sometimes. And I think now we have like all the, I've presented enough that it should be clear now what the answer to this is. So some people ask, okay, this view is wave function realism, but why do the wave function realists, or the people that call themselves that, wave function realists, understand the wave function as a field spread out over a high dimensional space and not a vector on Hilbert space? So some people do, like Sean Carroll wants to say the world is a wave function. Fundamentally, it's a vector on a Hilbert space, but that's not what wave function realism is, at least the way that jargon is, or that is used today. Well, there are two reasons for this. So there's two reasons why wave function realism, and the way I've been defending it, really should be a field on something with a structure of a configuration space, not as a vector in Hilbert space. So the first reason is that we saw that there are three arguments for wave function realism. The first two, the prima facie case and the argument from entanglement, could support, I think this is the case with the argument from entanglement, so I'll just say, okay, fine. Those arguments could support the vector in Hilbert space view as much as the field on configuration space view. But as we saw, those arguments aren't capable of giving us a reason to prefer wave function realism over all the serious rivals to wave function realism. The only argument that can do so is the argument from separability and locality. But that doesn't support vector in Hilbert space, the vector in Hilbert space view, right? Because that is not a separable metaphysics. You just got this one thing, this ray in Hilbert space, whatever that is. It's not a separable metaphysics. So that's not going to work. And so this, if you want to have the ray in Hilbert space view, you're going to have to give a different argument for that. And then the second reason is something I haven't really talked that much about, but typically the wave function realist, I guess I mentioned this briefly, this wave function realist isn't a nihilist about low dimensional ontologies. So they don't, although they say fundamentally the world of quantum theories is a world of a field and maybe some other stuff on a high dimensional space, they think that the low dimensional world in which we have this, appearance of non-separability and non-locality exists and it's real. It's just derived, or it's non-fundamental, or it's emergent from this high dimensional picture. And so if we're going to say that, we have to have the wave function realist needs to have some story for how wave function or whatever the fundamental high dimensional ontology is, how that can somehow give rise to this lower dimensional image. And this is a point Jill North makes in her Structure of the Quantum World paper also. It's just not clear how a vector in Hilbert space could do that. It doesn't seem to have enough structure to do that. I think David and Chris Timpson said something like this maybe in their one of their papers also. So the puzzle is, how to do that. So, David Albert has a proposal for how, if the world is fundamentally a field on a high dimensional space, how that can ground a world of objects in low dimensional space. I have another kind of proposal for that. It's very difficult for me to see how you're going to tell that story if you don't have this kind of structure of there being, things spread out in this other space, right? The fundamental space. All right, so that's all I wanted to say today. Thanks for listening.
Thank you very much, Alyssa, for the talk. Now, question, or we already have questions. First, please, Eric.
Thank you for the talk. I have a remark that leads naturally into my question. The remark is, I always get a little nervous when people say things like, this proposition is obvious, almost analytic. In fact, it's intuitive. Perhaps with the suggestion that someone who doesn't see that or feel that way has perhaps degenerate or malformed intuitions or something.
Oh, I don't see that.
And okay. I in fact, don't see at all why objects don't act where they are should be in some sense obvious, analytic, or intuitive. I would claim that for most of the 200 years between Samuel Clarke and Einstein, every physicist basically on the planet had no problem whatsoever with action at a distance. In fact, from about the 1840s onward, after Leverrier showed definitively that there were serious problems with handling mercury, and people and physicists at the end of the 19th century began seriously proposing modifications to Newtonian gravity, every single proposal was, let's change the exponent in 1/r squared. No one ever said, there's a problem with action at a distance, we better do something about this. No, so I am very reluctant to say that kind of consideration can be brought to bear here. But that leads to my question, which is that when you gave your definition of local, you said a theory is local if and only if it contains no action across spatial distances.
Yeah.
But as far as I can tell, the extra dimensions of these higher dimensional spaces are not spatial dimensions. So if you want to say they are, so it seems to me like you're facing the horns of a dilemma here. You either say, one, they're not, they're some configuration dimension, whatever exactly configuration is, or you say, no, they really are spatial dimensions. But then I think it's really incumbent upon you to explain why it is that they play no role, for instance, in general relativity, why we don't have to use higher dimensional manifolds when we're modeling extremely successfully phenomena that involve extremely, in regions of extremely strong curvature, like coalescing binary black holes. I find it absolutely incredible. I find it mind-blowing that there can be, that the world really is this unbelievably high spatial dimension space, and yet nowhere in cosmology or astrophysics does it ever show up. So I guess that's my rant. Thank you.
Oh, that was awesome. Thank you so much. Those are really great points. So on the first one, I mean, maybe you don't think this move is okay, but really what I'm trying to argue here is that these are intelligible to me, and I think to a lot of other people. And so I am not saying like wave function realism is the one true metaphysical framework for quantum theories. I'm saying that there are a lot of people who do find metaphysics that are separable and local intelligible. And those of us that do can get a lot of practical benefits out of having that kind of framework. So that's the move I want. And so I'm really like a pragmatist about this story. But can I just ask, like, so I feel like magic is like amazing when they can pull a rabbit out of the hat or have something. I mean, how do you explain that if you think that like action at a distance is completely intelligible? Like when magicians do magic tricks, like people pay money to see that and find it amazing.
If you're asking me personally.
Yeah, I'm asking you, like, what's up with that? You're just like, I don't care. That's the way the world is. Gravity.
No, well, yeah. For me, one, I think that actually there's no such thing as real magic, unfortunately. So I'm not going to try and explain magicians put rabbits out of hats. But for me, intelligibility is a statement. So I think, in fact, you and I may agree on this. To me, intelligibility is a statement about one's psychology. What you find psychologically comforting and useful is not what I may find psychologically comforting and useful.
Yeah, I don't know.
So that it sounds like you and I may completely agree on.
Okay. All right. So, okay. So yeah, but I appreciate that. And the point about physicists just, so the way, I don't know, the historical point I'm interested in though there. I mean, I thought that the history of physics was more like we saw that we didn't know what was going on with the metaphysics, but it didn't matter because physics could just set aside that issue and we have equations that work. And so we're fine doing physics. We can leave these kinds of natural philosophy questions aside and make progress.
I would be skeptical of telling that kind of story, at least in the 19th century, because people in the 19th century were very exercised to produce a mechanical model of the luminiferous ether. No one ever worried about doing that for gravity.
Okay.
James maybe has a comment on it. Do you want to comment on this, James?
James Ladyman?
Is that me? Oh, hello.
Yeah.
Hey,
Hi,
James.
I was just making a comment because hi, Alyssa. I just made a comment because Eric said he thought there was real magic, and I know that there's a notion of magic states in quantum mechanics. It's just a glib remark. My comment would be, now I've been invited to make one, thank you very much, that I don't think what we have in quantum mechanics is like pulling a rabbit out of a hat in all sorts of ways. And so it's perfectly intelligible that we would find pulling a rabbit out of a hat mysterious whilst accepting quantum entanglement. And indeed, you might think quantum entanglement is part of the explanation of how the classical world macroscopic objects behave.
I would completely endorse that.
Yeah, so my comment was sort of in the spirit of, I'm glad that's true, Eric, because it was in the spirit of sort of what I thought would be a rejoinder from you to what Alyssa said. Thanks very much.
Then we have a question from David, please, David Wallace.
Thank you. Thanks, Alyssa. I just wanted to think a bit more about the sort of metaphysical methodology in the latter part of the talks. So, I mean, here are a few sort of takes one can have on how to on what kind of question we're asking when we ask is wave function realism the right way of thinking about the ontology of the theory. So the most common way it seems to come across is sort of a straightforward scientific realism, where we want to say, look, there are multiple possible ways of describing the ontology of quantum mechanics, and they're incompatible, and one of them is true at most, and others are false. The formal mathematics underdetermines the truths. And on that reading, what's going on, it feels like intuition doesn't seem particularly salient. I mean, the issue would be why is the intelligibility or intuitive plausibility of something a reason to think it might be true? But there are different takes. You could have a sort of how I read a sort of object structural realism and say something like, well, it's factive what the mathematical structure of the world is, or what the structure of the world is, and that's given by the mathematics, but it's not factive how we describe that in object property language. And so judgments as to the right linguistic description of the theory can absolutely be driven by pragmatics and issues of intelligibility, and can be pluralist. And then you could have a sort of Van Fraasten style take, which says, look, we're just never in a position to know the content of the theory beyond its empirical predictions, and so by all means use whichever one you feel is most convenient interpretationally, but the theory doesn't really tell us anything truthful about the unobservable, even at the level of structure, let alone at the level of sort of what the objects and properties are. And there again, you could perfectly well have quite pragmatic attitudes to what the rules might be to assess different frameworks. And I think I mean, one of the things I get from your talk and also from your book is whatever your metaphysics of or understanding of the metaphysical question, it doesn't look like it's a straightforward scientific realism. It doesn't look like it's like one of these things is true. And intuitiveness might be a criterion in selecting which is true. But I'm wondering how you are seeing the question. What kind of question are we asking when we say what's the correct ontology for quantum mechanics? Is it just a pragmatic question, or is it more than that?
Yeah, let me just, I see a message from Eric also. I didn't answer the second part of Eric's question, so if there's time, I would like to say something about that, but I wanna, I'll answer David's because I have Eric's written down, so I know I'm not forgetting it. Yeah, I'm glad you asked this, because sometimes when I was presenting arguments against space-time, or sorry, responding to your arguments of why you couldn't be a wave function realist, you and Chris would both always say I can agree with this part. And so I feel like I'm glad I've been wanting to talk to you both about this more to understand better. So I do think that there is, I mean, I'm a realist, like a metaphysical realist, in the sense that I do think there's a fact about what's out there. But I don't feel like these, when we present our different views, like wave function realism, or let's just say wave function realism, primitive ontology people, just to be clear there, I don't feel like I am better in tuned with reality than Valia is, or Shelley, right? I don't think that I'm I have certain arguments, they have certain arguments, but I think that those arguments are, the best that they do is say here's how you can get a picture of the world that has these virtues. And when you have these virtues, you know, good things follow, and that's about it. I don't, and so I feel like I always wanted to say the same thing to you, the space-time state realism, and like to James and his ontic structural realism, but I feel like what you were just saying, sometimes it sounds to me like you're an ontic structural realist, and I feel like the metaphysics that you present for quantum theories, your space-time state realism is different than, I don't see it as being ontic structural realism. So when I'm talking about ontic structural realism here, I take that as a view that like fundamentally there just are these relations, and there aren't, you know, fundamentally it isn't like a field with these, properties instantiated at points. Where I feel like space-time state realism I take to be an alternative metaphysical proposal where you've got, these properties assigned to points in space-time. And so I mean, the way I'm seeing it is, so I take these to all be rival frameworks, and then the best way to address them is to say, well, what good comes from adopting this framework?
Okay, so different people use ontic structural realism in different ways. I mean, what I meant by just then was a sort of negative thesis in some sense, that two supposed descriptions of a theory which are mathematically equivalent don't disagree factively.
Mm-hmm.
So from that sense of ontic structural realism, it's not a factive question whether you should be a space-time state realist or a wave function realist. It's going to be a more kind of pragmatic kind of a question. Chris and my paper is rather carefully finessed in this regard. We say somewhere that on a sufficiently strong structural realism, this is not a factive question we're considering, but the sort of considerations that traditional scientific realists normally use to resolve supposedly factive questions like this are pretty similar to the sort of considerations one might use to resolve pragmatic questions of this sort. I mean, we give much lower weight to intuition, but again, if you're pragmatic about it, that could just be a different style choice. So I'm using ontic structural realism in that sense. So from that point of view, space-time state realism would be one of the various descriptive things you could say about the underlying mathematics, and I'd make a case that it's a more pragmatically useful and helpful version in most contexts than wave function realism, but that's something where reasonable people could differ. There's an alternative reading of our framework which says your broader metaphysics is something more like a straightforward scientific realism, whereby it's a factive question whether space-time state realism is true or wave function realism is true, and then there's going to be a methodological question about why issues of pragmatism and simplicity and intuitive appeal or something should be informative about that factive dispute.
Okay. Yeah, thanks. Okay, that's helpful. So yeah, so when I had ontic structural realism up there, I was thinking about, like, I don't know, like in James's like what is structural realism paper, when he's like, you have to understand this as a metaphysical thesis, as it's talking about, these relations, or, in Stephen's book or whatever. But okay, that's fine. That's helpful. I don't want to answer the question about, is this scientific realism? I think the best thing would be to say no. Like, this isn't. It's realism. So this is a framework for realism in the sense that it's a framework in which we take quantum states to be telling us things about the world. But what are they? Can we know that just by looking at by having these debates, exactly what they're telling us about the world? No, we can't. But we're starting with the assumption that that's what they're doing, right? And if we didn't start with that assumption, a lot of these debates wouldn't make any. I don't think they would really make sense, or at least it would. I feel like it would undercut a lot of what the arguments that have been given. So yeah. Thanks. Oh, can I go back to Eric, because I felt like I cut him.
Yeah, sure.
Yeah.
Yeah, sure.
Okay, it's because is that what he said in the chat? Oh yeah. So that the response to that was just that general relativity talks about the low dimensional image. And so I don't want to touch the low dimensional image. The low dimensional image is, what it is, how it's described in, whatever, space-time physics you want to talk about. And so this is talking about a more fundamental, when you have non-separability or you have non-locality in the low dimensional image, then the wave function realist will say, oh, that's suggesting this isn't the fundamental metaphysics. We need a more fundamental metaphysics that doesn't have that non-locality, that doesn't have that non-separability to ground that. And so the way I understand, or I'm kind of trying to defend wave function realism, isn't by saying, we should change general relativity to, talk about these spatial dimensions, right? It's saying there are those spatial dimensions, and then there are more fundamental ones. Now, I understand sometimes, so you started this by saying, that the account of locality talks about action across spatial distances, and you're like, the spatial distances are the ones that we learn about from our space-time, or from like GR, for example. And so this isn't the spatial dimensions. There, I'm saying they're not those spatial dimensions, but this is another kind of space. It's another kind of space in which there are different dimensions, and that is the space that's described by that the wave function realist is interested in. And so then, I think the natural objection after people make that complaint, then, the next complaint, when I say, well, it's a different space, then they say, well, I don't care about non-locality in that space, right? And so that's why I try to say, that's right. Most of the arguments again for local metaphysics don't work to defend this view. The only arguments that work to defend this view are the arguments from intelligibility that you don't like, but that's fine. I like them. And other people, I think other people like them too. So that's, anyway, I did want to respond.
Thank you. I just want to make sure I understand. So when you say that there's this other space, is it correct that there's no relationship between the two, or is it rather, because I had the idea that the 3+1 dimensional space-time that we seem to see around us was somehow supposed to be emergent out of this space.
Yeah.
But if that's the case, my question wasn't about whether we should change general relativity. My question was, how can general relativity be so successful in never taking, by completely ignoring these other dimensions when it treats phenomena where it seems like quantum effects become utterly non-negligible? One would expect that if there are these quantum effects that require these higher spatial dimensions in order to give their complete representation, and we have and general relativity is making predictions about regimes where quantum effects like coalescing binary black holes or very early state cosmology, these quantum effects become really non-negligible. It seems incredible to me that general relativity would make amazingly accurate predictions while completely ignoring higher spatial dimensions that were really there.
Yeah. Okay. So this is something. I mean, I want to think. This is something that I'm trying to think more about. There are, when we're talking about those regimes where quantum effects become non-negligible, and we want to, start talking about like quantum entanglement, how this interacts with what I'm proposing here. But I mean, my thought about that is just, you don't need to, there's no reason, just for the purposes of doing these physics, if you want to talk about quantum entanglement, and you're not caring about having like a story about how there could be this kind of, correlations between distant objects, then you don't need to come to wave function realism, right? Just for those purposes, right? You just leave it at this kind of, you stop at this, the non-separable story, I guess. But now, once you get into these kinds of more foundational issues where you're like, but how could there be these correlations? Then the wave function realist will come in and say, well, because those are manifestations of this more fundamental picture. So yeah, so anyway, that's the story. So there are certain kinds of purposes for which, we don't have to answer every kind of question or address every kind of puzzle. But when you're specifically puzzled about non-local correlations or fundamental relations that don't bottom out in terms of facts about, the relata, then that's when wave function realism comes in to address that.
Thank you.
Good. We still have quite a lot of questions, and we're slowly running out of time. So, Lev, please go on.
Alyssa, thanks.
Hi.
I think clearly separability and locality is very important. But as you mentioned, and I think some other commentator mentioned, we would like to have it in 3 dimensions. And the way just to go to 3 dimension, that doesn't seem like a real solution. But if you look on wave function realism, maybe a little more narrow that you looked at, you had the 3 things, Everett and then Bohm and GRW. If you take it in Everett, you have locality in 3 dimensions. There is whatever you do here, nothing will change there if you look on all words together.
Right.
So I think this is kind of, this is a very strong thing for wave function realism, and even because it has locality in 3 dimensions. And maybe kind of a comment that you said that no one defends wave function in 3 dimensions. I defend wave function in 3 dimensions, but of course only in 1 word. If you look on a wave function realism of all words together, there you need 3 dimensions. But inside this word, I am a wave function in 3 dimensions. I believe you too. Every macroscopic object in our world is a wave function in 3 dimensions. It has some part with entanglement, some relative coordinates. But what's important for our interaction, there are some kind of basic variables which are wave function. It's everything quantum. It's in 3 dimensions. We live in 3 dimensions. So there is a meaning for wave function realism in 3 dimensions in a particular word of many words.
Okay, so can you tell me where is the best, because I want to understand, I'm just not sure where would be the best place. Where do you write this about this view that we are a wave function in 3 dimensions? I've been wanting to talk to you about this. This is another thing I've been wanting to talk to you about.
I think you've been in a conference where I have a contribution, ontology of the wave function.
Okay.
Ontology of wave function, many word interpretation. All is psi. It's another paper.
I just didn't.
Mechanics and determinism is another paper.
Okay.
And my entry in the Stanford Encyclopedia really represents this view.
Well, okay.
So they present, try to present us as you too.
Okay, all right. Yeah. So the point about like Everett and locality, so right. So you don't have to go to higher dimensions to get locality in Everett. The idea though was that you still have separability or non-separability.
That's true.
Yeah. So that's, I mean, that's the point. And of course you can say, don't care. That's what we learned from quantum mechanics, is that there's fundamental separability. And I don't take there to be anything wrong with that. As far as that, that goes, you can pursue that. You just have to say, and here's all the good stuff that comes when you give up, right, this, what I thought was an analytic truth, right? And you accept non-separability. What I'm doing here is I'm saying, well, But the presupposition would be, which not everybody will agree with, but the presupposition would be we want to keep separability, at least in the fundamental picture, to explain any kind of apparent non-separability. And then, you know, once you go there, then you get stuck with a wave function in higher dimensions. But that's okay, because that was going to have practical benefits. Yeah, so I guess it isn't the case that when you have a, just being an Everettian, I don't think that makes you a wave function realist, right?
I think it is.
Okay, that's what, okay, that's why I'm always confused.
The only thing.
All right, that's where, okay, that's where, right, that's why, okay, because, yeah, so when I read you, I see you defending Everett, but I'm not seeing it, that I think Everettian quantum mechanics is compatible with different kind of metaphysics, and one is wave function realism, but like David Wallace here, I mean, he's not a wave function realist, but he's an Everettian. So I think, you know, you have to interpret Everett or Everettian quantum mechanics in a particular way to get to wave function realism. And the way that I'm using the expression is just like following David Albert and Barry Lower to call wave function realist interpretations of, for example, Everettian quantum mechanics, the ones according to which the wave function is a field on a high dimensional space. I grant that other people could be Everettians and realists about wave functions, but then that wouldn't be, you know, this view. It would be a different view.
But just so the only difference that I'll take 3D very serious. David Albert is ready to say it's illusion or some other trying to make it to have it emergent. I think it is a postulate. But when I have a postulate, so everything in 3 dimension. There are some non-separability, which kind of can, this is a fact of life. It's unfortunate, not that I like it, but this is fact of life. There is a non-separability in 3 dimensions.
Okay, all right, that helps, thank you.
So David, do you want to quickly comment on this, or we're running out of time? But
super quick. It might be helpful to distinguish, you know, wave function representational completeness, which arguably is just entailed by the Everett interpretation, from wave function realism, which is then a sort of concrete metaphysical thesis about how to make sense of that representation in complete wave function.
Very good, thank you. So we take one last question from Aurélien, and then I think we will close for today. It was a long day. And sorry for the others on the list.
So my question is about the benefit. First, thank you for your talk. Okay, sorry. And my question is about the benefit of the wave function realism that you mentioned at the end of your presentation, because what is at stake finally here? There's this kind of discussion about the dimension of space. So if you discuss about if it is better to work in configuration space or in 3-dimensional space, okay, this is an interesting point. There's also this question about primitive ontology, if the wave function is nomological or something else, okay, this is or more ontological, this is great as well. But finally, at the end, who cares really about the problem? Because in classical mechanics, you have already the same issue. You have different formalization, different formalism for Lagrangian, Hamiltonian, Newtonian formalism. They are all describing the same, exactly the same theory. And at the end, what is important is if this different formulation of the theory is giving different results. And I believe that if the different interpretation, different formulation of the quantum mechanics in configuration space or in a 3-dimensional space are leading exactly to the same results, so they are exactly the same theory. It's like translating a text into French or English is the same. If you translate well, of course, which is not my case, but then it's possible to have otherwise you have exactly the same theory. So I think it's better to think like what will we have after quantum mechanics? Then it makes sense to say, to have different view, different perspective on the same theory, and maybe then it can make sense for building something new. Yes, thank you.
Thanks. So, I mean, I think thinking about what's going to come next and what's going to be the next theory, I don't want to deny that that's a good way to look at the import of ontological questions. I just don't, I mean, maybe it's just, I'm a metaphysician. And so I think that there's more here. So I want an account of what the world is like according to these theories. And you can raise this. You say, well, I mean, what's the difference with classical mechanics? We have different ways of understanding. I mean, even if we stick with like the Hamiltonian formulation, we can ask, like, does that mean that we're going to take this higher dimensional space seriously or not? That's a question in classical mechanics. And like Jill North in her work tries to like make progress on how to kind of address the metaphysics of classical mechanics. For me, I think I'm not trying to, I'm not disagreeing with you that the theory is going to be the same, whatever. There are going to be these different formulations, maybe, but the theory is a theory, and answering, are you wave function realist, are you not, might not have an impact on what the theory looks like. Or it's not trying to have an impact on what the theories look like now. They're trying to make sense of the theories and what they tell us about the world. And I mean, that's just I don't know, that's the way we are. That's where we are right now. It seems like any way of giving a metaphysics for quantum theories at, the quantum theories that we have now that solve the measurement problem, those are what we're interested in. All of the accounts are going to give us some kind of weirdness, whether it's non-separability, whether it's higher dimensions, whether it's non-locality, and the weirdness that is still there in the primitive ontology view, where the only matter there is, has very little to it. They all have weirdnesses, and I think that's an interesting question of like, well, how should we understand the weirdness of quantum mechanics? So that's the project. I did say a little bit at the end when I was talking about the practical benefits of, well, if you take this seriously, then you might ask, like, is there physics of this like high dimensional space that might be interesting? But yeah, that's the.
Yeah, okay, no, in fact, it's true. The main point is that as a metaphysician, you need to think about ontology. Then the ontology is different in one space or in, but sometimes it's good to have also a perspective of Babylonian, like say Richard Feynman, so to have all these perspectives together in parallel and say maybe at the end it will help for future theory. This is what I wanted to.
Yeah. No, yeah. So I really don't want to I'm not just trying to dismiss that at all. I think that that's totally, right. And I think that in my book where I talk about these arguments in a lot more detail, I do say things like, well, maybe, certain theories of quantum gravity will make more sense, in the context of wave function realism than other approaches. But this is like super speculative, and I don't really, I just don't feel like well equipped to kind of go there. But I think that that's, when I was replying to you, I wasn't trying to deny that. It might be the case that certain frameworks for providing ontological interpretations of quantum mechanics will be more or less fruitful for developing future physics, right? I didn't want to deny that. I was just saying, in addition to that, I think, even if we set that aside, I still think there's an interesting question about the theories that we have. What are they suggesting?
I think it's very interesting anyway, so I don't disagree.
That's good then. Please join me in thanking again Alyssa for this talk and the discussion. Thank you very much. It was very nice. And I just wanted to say that there are going to be plenty of time for discussion during the 2 roundtables tomorrow and the day after tomorrow. So don't worry, plenty of time for further discussion. Thank you again, Alyssa, for the talk and the discussion. And just we reconvene tomorrow. There is a change in the program. So tomorrow we'll start with the Renato Renner's talk. See you all tomorrow. And thank you again for the discussion and participating, and yeah, all the best.
Bye-bye.
Bye.
See you tomorrow.
See you tomorrow.
Yeah.
Quitter la réunion.